Okay, so let's go on using our notion of dimension. Remember that the rank is the dimension of the column space. And you might wonder why we're spending so much time with dimensions and playing around with these numbers. But the fact is that when you solve systems of linear equations, the rank is a very important characterization of the type of solution space. You know, if you have the rank is equal to the number of columns, then you have no null space. And the rank tells you a lot about characteristics of the solution space. So we'll get more into that later when we talk about applications. But let's take a look at some more theorems that characterize rank. The rank of a matrix is actually the rank of the transpose. Okay, so we have this result. Okay, so let's then this really shouldn't be so surprising, because we have this theorem BRS, which I'm going to go back to. And this talks about basis for a row space. Now, we did this theorem before we defined basis, but it really was talking about basis. What this says is that if you take a matrix and you row reduce it, and you take the non-zero rows and turn them into columns, then they form a basis for the row space. Okay, so let me just draw that out a little bit. If I take a matrix A and I go to RREF, and then I'll get to matrix B, I'll get some stuff up here with pivot columns and so on, and then I'll have some zero rows down here. Okay, so it turns out that these non-zero rows, when turned into columns, form a basis for the row space. Now, how many non-zero rows are there? Well, there's the same number as there are pivot columns. So the number of rows that span the row space is equal to the number of pivot columns. But what do we know about the number of pivot columns? That's exactly the dimension of the column space. So the dimension of the row space is equal to the dimension of the column space. So that's actually the key fact in what we're about to prove, that how did that happen? So that the dimension of the transpose is equal to the dimension of the matrix. Okay, so that's what we're about to prove. I don't know why this is doing this, but okay. So the dimension of the column space is the rank of A. So we know that by definition. Okay, and that's R by by hypothesis. That's the number of pivot columns. Number of pivot columns is the dimension of the row space. The dimension of the row space is the dimension of the column space of the transpose. That's how we did it. We took the row reduced form, we took the transpose, and the non-zero columns gave us a basis. Okay, so we're simply relating dimension of column space to dimension of row space, and dimension of row space is the same thing as the rank of the transpose. Okay. All right, so some examples. If you have a 4 by 7 matrix that reduces here, what's the rank? Well, 1, 2, 3. Okay. If instead you took the transpose and row reduced, you would still get 1, 2, 3. Okay, so we could tell right away from here that the dimension of the row space is 3, but you could also take the transpose and row reduce and show that the dimension was 3. All right, so now we can relate all of these dimensions together. Remember how we found that null space, column space, row space, and this is the left null space. And you can get these from this extended reduced echelon form. Remember, you had something like this. And this had zeros down here. You can go back and take a look at this. And this matrix was in reduced row echelon form, and these rows formed a basis for the row space. And this matrix down here was also in reduced row echelon form. And we could use this to find the left null space. So you can just compare dimensions. If we have an m by n matrix, this is m, and this is n. Remember, we tacked on an identity matrix, so that's n also. So we can simply count dimensions. This is the number of non-zero rows, so that's r there. So that means that this must be m minus r. So that means that the dimension of the left null space must be m minus r. So that gives us all the results. The dimension of the null space is n minus r, which is the number of non-pivot columns here. The dimension of the column space is r, which is the number of pivot columns, which is the same as the number of non-zero rows. The dimension of the row space is r, and the dimension of the left null space is the number of vectors left over here. Okay, so we have all these dimensions following simply from the reduction of the extended row echelon form. Okay, and that takes us to the end of this section.